I like to think about functions on two variables very visually. And even in some of the previous videos, we've gone on and talked about the graph of a function on two variables, taking the point in the domain x comma y as being in the plane, and then using the z-coordinate to plot a height either above or below. In this video, we finally define what we mean by graph rigorously. F of x comma y is a function on two variables. And then we're looking at a set of points in space, x comma y comma z, where that z-coordinate comes from the function value, f of x comma y. That set of points in space is called the graph of f of x comma y, and we also call it the surface, z equals f of x comma y. The set of points in a domain, where f has a constant value. So if we set the function itself equal to a constant, we get what is called a level curve in the domain. And I want to take a specific example to examine these two definitions. I want to take this set of points. I want to take this function on two variables, f of x comma y equals 2 minus the square root of 4 minus x squared minus y squared. Pause the video here and see if you can identify this surface before moving forward. Okay, so if you just looked at this and you thought about it, maybe you figured out what it was. Let me give you a hint. Cover up the 2 and let it be a z equals. We've looked at a surface like this before, and then imagine adding 2 to it. If I cover up that 2, that is the bottom half of a sphere. If I add 2 to it, I can actually think in terms of my transformations of functions. If I had the bottom half of a sphere, so a sphere below the xy plane in my hand, I add 2 to it and it all moves up 2 units. It'd be a sphere of radius 2, so it would be a sphere that just touched the xy plane at the origin. In fact, here's its graph. So I have a hemisphere, and a little hard to see on the video because it's a clear hemisphere, touching the origin in the xy plane and then rising up out of it, and I see that it's 2 units above the plane. If we didn't believe that this was a hemisphere, we could actually kind of work backwards. I could take 2 away from both sides. I can imagine squaring both sides. And this is where my equation stops really being about the bottom half, because when I square both sides, I lose this information about it being the bottom, right? Because it could have been the positive part when I get 4 minus x squared minus y squared. And if I get the x squared and y squared on the other side, I'm looking at the equation of a sphere. Well, since I have a graph here, and now we know exactly what it is, we might as well write down the domain and range. The domain, the set of all of the points on the inside of the circle I have sketched out there. And we could actually set what's under the radical, bigger than or equal to 0, to deduce that. So everything on the inside of that circle of radius 2. And then the range, well, I can see that I get 0 out, and I get all of the points on the sphere that have z's between 0 and 2. So there's my domain, and there's my range. Now, that last definition we saw is probably a little smudged now that I've dropped a board on top of it. If I set f of xy equal to a constant, I'm supposed to get what's called a level curve in the domain. So let's just look at that idea. So let's let z equal 0. And what I realize is my range is telling me the possible things z can equal. So 0 is literally the smallest thing I could imagine z equaling. Well, here's my function, f of xy equals. I've written it as a z equals. So 0 equals 2 minus the square root of 4 minus x squared minus y squared. Well, now I have a function on two variables, and now I understand that definition a little better, because that definition told me that my level curve lived in the domain. Function on two variables, I'm getting ready to draw a curve in the domain. I can imagine adding the square root part to the other side and then squaring both sides. And I would get 4 is equal to, let's see, square both sides after I add that, that's 4 minus x squared minus y squared equals 4. Take 4 away from both sides, multiply by a minus 1, I get x squared plus y squared equals 0. The only point that does that is the point 0, 0. That was that point where my sphere just touched the xy plane, so I've colored it in purple there, a point at z equals 0. Let's repeat that process. Let's let z have a different value. So I'm going to erase where I just did my arithmetic there, because I'm going to do the same kind of arithmetic again. But this time at z equals 1. And we'll just see what happens. At z equals 1, I would have the equation 1 equals 2 minus the square root 4 minus x squared minus y squared. I can imagine taking 2 away from both sides. And I have this impulse to multiply by minus 1, but let's just go and square both sides and skip a step. Take 4 away from both sides. And what I have here is the equation of a circle with a radius of the square root of 3 centered at the origin. The square root of 3 is about 1.7, so something like here. Just drawing that circle centered at the origin with a radius of the square root of 3. We're just going to pretend that's a circle. All right, and then I could imagine plugging in the largest z value I could of 2. And that's a good exercise. You should go on and do it, but I think you might have already guessed what's going to happen. We're going to get the outside edge of the sphere, or the outside edge of the domain, right? The boundary here, right? What is the equator on the sphere was right above this circle. Those are my level curves in the domain. I plug in that point, I get out 0. I plug in any of these points and I get out 1. And what I'm thinking about here is a topographical map. Everything on this circle is 2 units above the plane. Everything on this circle is the square root of 3 units above the plane. Excuse me, is 1 unit above the plane. That's a circle of radius root 3. And everything on this circle is 2 units above. And so I bring my hemisphere back in. Right, and I could actually imagine drawing out all of these points 1 unit above the xy plane on the sphere itself. Right, drawing a red circle above that red circle. In the domain, here, the red circle is called a level curve. When I draw it on the sphere itself, it's called a contour curve. Level curves live in the domain. Contour curves live on my function, on the graph of the function on the surface. Now, let's imagine that we were going to look at a typical level curve in the domain, or even a typical contour curve on the graph. So instead of picking a specific z, we're just going to say, hey, we're just going to set this equal to some constant, and the only thing I know for sure about that constant is that it's between 0 and 2. So c would equal 2 minus the square root of 4 minus x squared minus y squared. Take 2 away from both sides. Square both sides. Take 4 away from both sides again. I don't know why I said again. We took 2 away from both sides, but we're just going to keep going with it using that same methodology. And this is kind of a messy thing, but I can imagine multiplying both sides by a minus 1. I get x squared plus y squared equals 4 minus a number. So what I really have here is x squared plus y squared equals a number, which means this is the equation of a circle. Maybe a point, but what I would claim from this is the typical level curve is a circle. So now I know if I want to have constant values of z, I input circles. And one way to think about that is if I draw circles around the origin on this hemisphere, I'm always a constant height away from the xy plane.